Welcome everyone to the Designing Your Data, the bread and butter of IPL performance talk by Aaron. We're glad that Aaron can join us today. So yeah, without further delay, over to you, Aaron.
This talk is called Designing Your Data, and this is something that's come up in the history of me giving talks about how to write APL code. But in this talk, yes, we are sort of in the context of APL here, but there's going to be almost no APL. Very little squigglies, because this is really about data. But before we get into that, primarily, I want to do a little bit of background of where I'm coming from. So I do a lot of APL programming. And for those who know, APL is the language with all those funny symbols. And so most people, when they see APL, they see this and they think, oh, all those funny, crazy symbols. But we're not going to do that. We're not going to actually talk much about the symbols at all. I'm not going to explain any symbols. We're not going to do anything like that, but it is helpful to know conceptually, what is APL as a language? And conceptually, we can think of APL as a very rich economical vocabulary for computing over arrays. But there are other languages do that. So what sets APL apart, sort of in a big way, is that APL has a killer syntax for doing this. Now, one of the problems that comes up when you talk about APL, or when people start to use APL or think about using APL or try to learn things from APL, they tend to focus on the symbols. They tend to focus on all of those, the thing that seems to make it unique, which is its syntax. But the syntax isn't everything, and the syntax is built over a domain, and you need to think about that domain as well. So what happens is beginners tend to get stuck when the problem that they're trying to work on doesn't match arrays. It doesn't feel like it's a natural fit. So it doesn't feel like it's an array problem. And this is worse the more people are used to solving problems without using arrays. So a lot of programming languages today don't reach for arrays as their core modeling tool. A lot of times you reach for a different abstraction tool to think about modeling your data. So that means that today more and more people find it more difficult to think about the problem that they're working in arrays. And if we look at how experts work on APL, one of the key things that they do is, yes, they're very good with the symbols and the syntax, but they use that symbology to work with their data. So they have a really strong laser focus on what their data is and how they're working with their data. So they tend to encode their problem somehow into the array model in a way that makes it very simple and efficient and everything like that. So experts are very good at encoding the data for simplicity and efficiency. And what I want to talk about today is how do they do that, right? So if you've got this language for working with arrays, how do you actually encode your data? What do you do to design your data? And I want to focus on the ground level for this. So I want to think about this in terms of sort of the foundational building blocks. Rather than start at a high level, we're going to start really low level and think, what are tactics for data encoding that we use and leverage in APL all the time? So what does that look like? And let's go through this. So we need to start with even below the layer of our tactics, we have the foundations. And you would have expected me to put the array model here first, but I'm going to throw a little surprise in here, hopefully, and say, let's start from the relational model. And experts in APL tend to be really good about thinking in terms of the relational model, at least implicitly. They may not realize that's what they're doing, but the relational model pairs in with the array model really critically. So what I mean by a relational model here right now is the concept of tuples organized into tables where each tuple has a set of fields and the table has a header describing the types of those fields, right? And what you layer on top of that relational model is a language for manipulating relations. And there's a really interesting element about this, which is relational variables. And I want to highlight this because this will sort of tie in with what we're doing later, is relational variables are the named components. The thing that we sort of name in our system when we're doing relational thinking is the tables. we tend not to name the individual elements, but we name the whole table, right? And that has a lot of correspondence to the way you want to think about problems in APL. And it just so happens that APL is an excellent extended relational algebra for working in the relational model. So if we take the relational model and we also add on to it the array model, we get what the core foundation that we want to work with is. So the array model, we're not going to talk in detail about it, but the basic structures of the array model is that an array is composed of elements and a shape. And the elements are arranged in this shape in some fashion. And we don't really care exactly how they're arranged right now, but they're sort of arranged into various shapes, and they're rectilinear shapes. So there are different dimensions. The total number of elements we call the count. The number of dimensions we call the rank. And the first dimension we tend to call the tally. And we also, in the APL model, allow for nested arrays. So arrays can contain other arrays. And if we think about this in terms of how we might define this struct in a C-like language, we're thinking about an array having some rank and some shape, and then some array elements, right? And the way this works in practice, we don't have to get into all the details, but you want to just conceptually think about arrays as arranging objects in a rectilinear space. So that abstraction immediately comes to the first tactic. And this is the easy tactic. This is the tactic everybody knows. Choice number one, if your problem happens to be inherently dimensional or rectilinearly dimensional, rectangular, cubes, whatever, if you can fit it into some kind of space like this, do it. Like this is the best way to arrange your problem if it just naturally fits into this slicing model. And so we can think of different shapes that you can form that are rectilinear. And in APL, we have a scalar, which is just a single number or a single value, single array with empty shape. If you have one dimension, you've got a vector. That sort of corresponds to a line. There's one dimensionality, one range of dimensionality. A matrix has 2 dimensions. A cuboid has 3 dimensions. And we can keep going up into higher and higher and higher dimensions. And what we can use as a base is we can leverage that dimensionality to arrange information of our problem using that shape. So some classic examples is you often will say, well, if you have X, Y, Z coordinates or RGB values, you can arrange them in a matrix. And so our X, Y, Z, we could arrange for one row to have all the X's and one row to have all the Y's and one row to have all the Z's. And that allows us to have these little slices of all the values. But we could also arrange this where the RGB values, for instance, instead of X, Y, Z's, are put into columns. And then every row could represent a single pixel on an image, for instance. But we can also do things when we increase our dimensionality. So oftentimes, for instance, if you think about images that are playing in an animation, well, those are 2D images that are playing across time. That's naturally a 3D object. And you see 3- and 4-dimensional objects very commonly in machine learning algorithms where you layer data into these multidimensional tensors. And that works really great if you can fit your data into this model. But what happens if you can't fit your data into this model? Well, that leads us to our next tactic. And most people, when we think about this, do not immediately think of aggregation. What in most programming languages, you optimize for what I call reified object references. So you make an object, which represents sort of a single item, and you have a reference to that object. Usually that's a pointer to the allocated space in the garbage collected language where that object sits, and you reify it. And by reification, we mean that you make that object visible in your code somehow. You give it a name, you put a variable to it. It feeds in it as an argument or something like that. And a classic way you might think about this is here's an example of a bunch of different objects. We actually have 4 types of objects here. We have A, B, C, and D objects. And we have 2 B's, 2 C's, 2 D's, and 3 A's. And in a classic way that we might think about this is we take each of these objects, and each one of them has a tag, and each of these blocks are independently allocated somewhere on the heap. And there's a pointer to every single one of these objects sitting around, and we link all of these objects together using pointers to various places. And all of these objects now sort of sit somewhere on the heap, and our garbage collector will take care of this for us. But we don't control any of this, right? We don't control where the layout is or anything. So instead, in APL, instead of allowing all these objects to just sit everywhere, we aggregate objects and we start arranging them according to types. And this is the first layer into a relation. We start to create these relations that define all of these different types of objects. And if you're familiar with arena allocators, keep arena allocators in your mind while we're doing this. What we're doing is essentially the same thing as doing arena type allocation, where we are putting objects explicitly into these well-known boxes of similarly typed objects. If you're familiar with big bag of pages, garbage collection techniques, it's the same basic idea. And we're leveraging this to organize our data according to aggregate sets of items that have similar properties, instead of just having each individual item sitting around somewhere on the heap. And this has a lot of benefits for us. And if we do that, well, now we've got tables, we've got all these relations. So that leads us to our next tactic. We call this the inverted tables tactic. So here we have one of these relations with 4 fields, and each of these fields might have a different type, and we have 6 elements in here. Now, a typical way that people might organize this stuff is you could just put a matrix together, a single matrix, 2 dimensions, a 6x4 matrix, and then all the elements, all the tuples and fields go in there, and that would work. But it's very common for all of these fields to have different types. It's also common that you might want to independently allocate these things. So another common way that people will organize this in other programming languages is you get what's called an array of structs, or an AOS representation, where you have this vector of the 6 items, and each item is its own object, right? And so this is sort of the non-aggregate model here. And that's one model that we can arrange it. This one on the left is another model, but all of these have the cost that if F0, 1, 2, and 3 are each of their own type, we kind of have to merge or have a structure that understands all that different typing. And there's a lot of tags and everything that sits around. So instead, we can use something called the inverted table. And it looks a little bit different. So let's zoom in on that. And this is the same thing, but this time we've inverted the way we're representing the tables. We're using a column store representation for the relations. And that means that now at our top level, we have a vector, but that vector only has one element per field. And then each field contains a vector containing all of the field values for every element in our relation in one vector for that specific field. So each field is independent of every other field. And one of the really nice benefits of doing this is that you tend to only need to think about one field at a time very often, or you only need to think of a few subsets of fields for a set of objects instead of looking at all of them. So this has a lot of cache locality benefits, but we get even more benefits because of this next tactic. So we take these inverted tables, we can leverage implicit data structures that we can hide inside of arrays that give us some benefits. So in the case of inverted tables, the first one is the fact that the APL runtime is aware of different sizes or ranges of your data. And so every field has a different type, and each element size can be different. And since the APL system can arrange all of that data according to specific known types, it can now allocate limited amounts of space for each column independent of every other column. So if you have a column that needs doubles, every other column now doesn't have to have doubles, right? So if F0 only needed 8-bit ints, and F1 only needed characters, and F2 needed full generalized pointers, but F3 was just doubles, each of those could be allocated and given their own independent type and only need to consume as much space as they actually need, rather than having to have some size that can accommodate all the different types and have more tags and more data and more metadata all sitting around. So as in one example here, we've got a set of data that requires doubles, so every element takes up 64 bits. But if we have a vector that only has a short range, then we only need 16 bits. And so we can store each of these elements in a compact, packed way with only 16 bits. And APL also has native support for bit vectors, which means if we're only working with Boolean data, we only need to store 1 bit per element. And this is the kind of explicit or implicit data structure that you can have, but there are a bunch of other ones. So here's another example. Let's say we want to add more things to the end of an array. Typically, concatenating to the end of an array, you've got all your original elements, and then you've got the ones you want to add. Typically, this requires constructing a new array element and concatenating to the end. But we know that there's a more efficient way to do that. And oftentimes, you have to have a structure that's typed to know that this happens. In APL, we just sort of say, well, there's a syntax. And if you use that idiomatic syntax, we know that we can do this. And so what we can do is we can pre-allocate additional data so that every time you re-execute something like this, you don't have to do the allocation and copying over and over and over again, which gives us that amortized, efficient catenation to the end of a vector without needing to explicitly talk about that feature in the code or have a separate type that represents it. That all happens behind the array type. So it doesn't change our interface at all. And it gets even better. But wait, there's more. So we can also do this with tables, dictionaries, hash tables, things like that. So if we have something like a vector with all of these terms in it, we might want to look up whether a term is in that vector as a set, or we might want to find out the location, the index of that term in that vector. Any of that, instead of having to have special structures like lookup tables, hash trees, hashes, trees, B trees, all these things, or different ways of thinking about that, we can all say, well, it's just an array. We've got this lookup function called iota. And behind the scenes, whenever we want to look this up, we will create a hash table associated with this array and use that hash table behind the scenes to do the lookups efficiently. So to the language, we only see arrays, but underneath we can leverage all of our typical search and set and other algorithms like binary search without having to expose that above the array level and without having to create new types to talk about it. So if we then take that and put all of that together, we get one of the most useful things that we can see, which is interned data or symbol tables. So it's very common in a language that you will have explicit support for symbols. So a language like Scheme, the Lisps are really famous for having symbols, and those symbols are sort of first-class objects and entities, and you can compare them for equality, things like that, convert them to strings, etc. But all of that means that the generality requires that you provide a general system. But we can be more specific. We can be more limited. And so we can say, well, we have this vector, right? And this vector has some duplicate names in it, and it's some strings. And if we represent that vector, we've got a pointer for each sub vector that appears in this vector. So it's a vector of vectors, a nested vector. And each of these objects requires their own objects to allocate each one. So we've got all this duplicate data, right? And other languages know about this, like Java, they intern their strings, things like that. But instead of doing it automatically, we can do it explicitly because that means we can restrict our range. So in this example, this vector here needs 5 pointers to point to all the elements. And it also needs 8 bits per character, right? And it has 2 characters per these elements. So if we follow all that through, we get to this calculation of needing 400 bits for this for this. But let's see what happens if we change that representation and do something a little bit differently, right? Now we have a symbol table. And that symbol table only contains the unique strings that we have in this particular case. So this might be something that we use over only a single column of data, right? And in that case, each of those, we can now, our original 5-element vector can now point to one of these elements, right? And that means that each of these only requires 8 bits to store. So that gives us 40. And then if we calculate the space for this in the same idea here, but just with 3 elements, we get 240 bits, which is 280 bits. And that's 70% of the original 400 bits. And the bigger your tables get and the more duplication you have, the better this actually is, right? And I'm not calculating the sizes of headers and here's, but that actually makes the problem worse if you calculate in headers. So the benefits here are that you get this really nice efficient set. You can easily see all the names that exist, but you get this really efficient small range vector that only needs 8 bits per element or maybe 16 bits per element to represent all of the different things. And now your symbols, where they would represent symbols using 64-bit pointers in your typical representation somewhere because they have to represent symbols generically, of course, all types. Now, our symbols for this one context only requires 8 bits per symbol, which means that we now can fit that into cache easier. We can look things up over it. Our hash tables are faster. Everything gets faster just because we did that. And that's sort of a big deal. And it's layering on these tactics that you begin to see we start to get compounding effects. So you'll notice in this representation, each of these 0, 1, 2, 1, 0, they were actually indexes into another vector or into some vector. So they represented indexes. Well, that's a technique known as pointer vectors. And in APL, my recommendation is avoiding generalized pointers. So typically, references, names across all different systems, those are generalized pointers. And you tend to proliferate generalized pointers, which require 64 bits to represent all over your system. So in a typical system, you've got objects that link to other objects all over the place. And each of these objects is independently allocated. And then all of the references are a generalized 64-bit pointer pointing all over the place. In APL, we can do better. In most language, you can do better than this by using type-constrained explicit pointers with restricted range. So what does that mean? Well, the explicit pointers is pretty straightforward. You have explicitly, you lay out these pointers inside a vector inside your system somewhere. But what does type-constrained and restricted range means? Well, let's think about our objects and realize that oftentimes not every object has to refer to every other object everywhere. Very often, objects only refer to other objects in a small cluster. There's this little cluster of objects that all point to each other, but don't point to anything else. And they fit a certain type or a certain range or something like this. And so by putting them all in these arenas or boxes, again, arena allocation, you can say, well, all of these things need to point to each other, but we don't have to worry about anything else. And by putting them into these boxes, we can now create pointer vectors where we create all the edges for the system by pointing to elements inside of a vector that's all of limited range, restricted range. Now, why might we want to do that? Well, if we expand this example out a little bit more, and we look at the numbers, the IDs of these elements. So I've arranged these objects in depth first pre-order traversal. And if we have each of these objects arranged like that, down here, each of those objects exists as one of the elements in this vector. And now each of these pointers can point to something. So 0, we have 0 pointing to itself, just as a convention. And then 1 and 4 both point to 0. And then 2 and 3 point to 1. And 5 and 6 point to 4. Now, if we look at that, the number of elements here is very small, which means we don't have to use a full 64-bit sized pointer to point to everything. Instead, we can restrict the range of our pointer to only point into things that we care about. And by making these explicit, restraining them to only pointing to this small range, we get a lot more flexibility in how we represent the pointers, and we can limit our pointers so that we know that they're only pointing to certain valid objects in this certain space. We can usually restrict the range so that we don't have to use 64 bits. It's very rare to need 64-bit pointers to actually represent all of your data structures in these. Very often you can use 8-bit pointers or 16-bit pointers or sometimes 32-bit pointers, and you don't need the full generalization for most of your objects. And you save a ton of space, you make everything faster, and you don't actually lose anything in terms of how easy it is to work with. So let's say that we have one of these structures, right? And we've got all of these different types. So like 1 and 4 might be a certain type, and 2 and 3 and 5 and 6 might be certain types, or so forth. Well, now we have this arena of objects, and maybe we need to now tag them because they're different types in each of these objects, and we want to track that. Well, again, we want to leverage this inverted table concept, and instead of thinking about individually tagged objects, we want to think of aggregate tagging, right? We want to think of the type as a separate column in your relation, and you want to think about a whole vector that represents the type of all the different objects that are related to one another, right? And why do we want to leverage that aggregation? Because it allows us to reason about our objects as if they were tables or as if they were full things. So we can ask, well, I just want all the objects of type A. I want all the objects of type A and B, right? We can leverage the full APL syntax. We can build up things like this lower one, which is a histogram of all the objects. So we can see how many objects exist by what given type in a given arena, a given relation. And this merges two worlds that are usually disjoint. So it's very common for systems to have like, well, we've got our relational RDBMS data, and that stuff works this way, and we do global queries over it stuff. And then we've got all of our other objects, which are in our other programming languages, and they're individual. And we can't think about them aggregately. But if you represent your data using this aggregate stuff for everything, or for most things, then the type of SQL type queries that you might want to do over your objects to reason about them or to work with them, which sometimes is a very efficient way to work with some kinds of data. Now, that's what you get. And you can do that for all of your data instead of just having to decide when it's going to be this or that. So you can think relationally about all of your data or aggregately about all of your data. And this gives you a lot of power because now certain things can become really fast. And you can get you can do certain operations that you would normally have to traverse the tree to get. You don't have to traverse the graph of your object space to get to that data. And instead of traversing over and over and over and testing and walking and everything to find your data, you can now work with your data as large sets and just do queries over it, which is very powerful. And this now we're getting to the territory of where this starts to become, you start to leverage this into a real art. And one of those is that beginners often try to find the perfect representation. They tend to limit themselves and they think, okay, well, my data is represented like this. But we have this concept of a view in relations, right? Where we can sort of have a virtual view of our data. And there's no reason that you can't and shouldn't do this on all of your data. That should be a tool that you can use for everything. So instead of trying to find the one single perfect representation that's general enough to handle all your cases, maybe pick the representation that has the ideal characteristics for what you need it to do in any given context, and then just convert from the various representations. And if you have encoded your data efficiently, like using these previous techniques, which shrinks the amount of data processing you have to do, now this conversion can be really fast, and you get ideal representations of your data bespoke to each of your contexts, and now your code can be simpler. Everything can be easier simply because you're not afraid to switch the representation to what you want in the moment. And the one that I'm really, that I tend to use a lot is when I'm working with tree data. There are two very common representations of this. So like if you're working at XML or JSON or any other kind of tree data, I use it in the compiler. You have like a parent vector, which is the pointer vectors we talked about before, going back and forth. But the amount of bits you need per element to represent that generally scales according to the cardinality of your tree. So the more elements are in your document or your JSON tree or your syntax tree, the more likely it is you're going to need a larger set. So seeing 16-bit and 32-bit parent vectors are very common because there's often a lot of elements in the tree. And so you need to represent that. The advantage of that is it gives you a lot of flexible power to traverse the tree very efficiently. But let's say you don't need to do that. And let's say you only need to do a single traversal over a certain pass, or maybe you need to store the data, or maybe you need to work with groups of data in a different format. Well, the depth vector works. If we arranged this tree in depth first tree pre-order traversal in this certain ordering, and we put the depth of each element instead of using its parent, right? Now we've encoded the same information, but we only need to represent the highest depth that we have. And very often with problems, your depth is fixed or it's constant, and it's usually very, very small. So even though the cardinality of your object space might grow linearly, very often the depth of that space will grow logarithmically. And that means that chances are the depth vector representation will be really, really efficient. And so you can do this for transference or serialization or all sorts of other things where now your object is very efficient to represent. It's much faster to read in from data. It's much faster to cache. And for some problems, it's much easier to think on a depth level instead of on a parent level. And there's no reason these two representations can't simultaneously exist at the same time. You don't have to commit to one representation or another. Whereas in traditional data modeling, you usually commit to one representation or another, and you don't dynamically and explicitly switch between them with facility. So how do we then extend this even further? And Boolean masks are one of these like data-directed concepts that you really have to leverage in order to do good APL. And so since we have this really efficient bit vector mask representation where every Boolean only takes up a single bit to represent, we can use it to talk about, to layer an additional view on top of our data and talk about it in really interesting ways. So here, if we've got a simple piece of text, we have two different bit vectors that can talk about aspects of this tree in a very efficient way. One, we can create these boundaries where we have these groups for each of these objects, including the spaces. So we partition this text up without actually ever touching the text. We just have this efficient little partition that's a layer on top. And then we can say, well, what about the non-space values, right? The printable characters. Well, we can have a representation of that. And we can then use these to work with our data, oftentimes without ever actually having to touch the data. And it's much more efficient to work with these bit vectors because they're so much more small. They take up less space, they're much more cache friendly, etc. But we can also do this with other things. So for instance, in this case, Booleans are an if then else, right? And so one of the techniques that you can do is if your data is numeric, and you want to choose between A and B, instead of traversing and doing an if-then set, if you have an M mask, a Boolean mask that says whether to choose A or not, you can say, well, if A times M, that's going to give you all the A's. So in other words, you choose A if M is true, and then you choose B if M is not true. And you simply add those together because the multiplication will mask off the will mask off the irrelevant ones. And when you add it all together, 0 plus whatever will select everything. So you can select these all together. And similarly, we can use a mask to shrink our selection down, do some operations over it, and then explode it back up to the same size and work with it. And these sort of concepts that we work with are very useful for reducing the working size of what we want while not giving up the benefits of aggregate objects, right? Now you might say, well, oh, this A times M plus B times not M, that's kind of a trick that only works if your data is numeric, which is true. But if you've been paying attention, you'll notice we have systematically been re-encoding most of our data into numeric types of data. So now this trick suddenly works on way more types of data than you might think because of the way we've chosen to encode it. And now this technique becomes viable across the board. And if we leverage this even further, we get this idea of keys. So if we combine these things together, these tags, these enums, these views, these masks, etc., we can use the concept of keys, ordered keys, to do operations. So here's a simple worked example off of the mask case. Let's say we want to reverse each of the words, but we want to keep the words themselves in the same order. Well, we can use this bit mask, filter out all these and reverse them. So, and use these keys here. And so we've reversed the keys and we've reversed the string and taken out the spaces. And this mask in the middle will let us do that because we're only working off of the ones in this case. Now, if we do that reversal, notice that these keys, since they're reversed, well, they're also ordered. So if we use a stable sort, we can resort this using the keys that we just used. And now all the words are put back in their order, but all the words themselves are reversed. So then we can use this middle mask again and expand this little structure back out and put the spaces back in. And we're all good. And so we've sort of combined views and bitmask and keys and all of this together. And now we've got this very nice thing that's very efficient to work with because you're working off of these very efficient vectorizable structures. And we don't have to link and walk and traverse and everything like that. And we can just make it all parallel. And so this is a very efficient way to do certain operations in APL by encoding the data correctly and leveraging things like keys. Now, if you'll notice, one of the things we used in that last structure is ordering. And all arrays in APL have what's called a total array ordering, or the tau. And that means that every array can be ordered according to every other array. And if we leverage this, we can get some really, really powerful examples. Now, this starts to get into some pretty advanced territory. So I'm going to walk through the general intuitions here, but I don't want to go through all the details because it starts to get complex. But let's look at a case from a real world problem where this can become useful. So let's say we're trying to find where we are referencing names in this sort of like, so this A is a reference before this A is bound. So this A actually refers to the A up top, and this X refers to this X up top, and this X refers to that X up top. But now we've bound A here. So this A refers to the inner A, not the outer A. And then these two A's and B's refer to the inner A's. But this G, it doesn't refer to anything up. It's actually a forward reference. So it actually has to refer up and out and forward, right? So how would we do that? Well, one method is to traverse our tree, looking at all these tokens and everything, and do the lookups and track our environments and all that. That works. That's fine. There's pretty nice ways. But let's think about this differently. We can also think of each line has a certain ordering. So if we reverse the ordering, we can say that if we go from right to left, we can say within each line, this A comes before this A, and this X comes before this A, right? And in each line, we can sort of put an ordering on it. And then we can put an ordering on all the lines. This line comes before this line, comes before this line. Those are two separate orderings, right? And then in here, we can say, well, these orderings, because they're at a higher nesting level, those come before these orderings. And so that's another one. So that gives us three orderings, basically, right? And each of these three orderings, if we put them together, we can sort that using all three orderings together as a lexicographical ordering. And that's a single operation in APL. And if we do that, we can apply an ordering, create a permutation vector. So this lowest element here is a permutation vector of these various elements that puts them in that order. And now notice that this A here corresponds to this first inner A. And then this A refers to this inner A. And then the final A refers down here. And now, if we want to look up the where we have zeros here, these are the references, and the ones are where we have definitions. So if we want to look up the value of a given reference, we can just go back and start searching left. And notice that this A will never see the other two, or the other A definition, right? It'll only see the definition for the outer A. And we did that simply by arranging the ordering. And you might say, well, why would we do it that way? Well, that operation of looking for our slot that we want to find in this ordering happens to exactly correspond to a single APL primitive that we have. And so now, if we map this data correctly into the correct ordering by using the tau, by using permutations, we can arrange it so that we can leverage all of that implicit structures, the binary search, all of that, and make this lookup really efficient. And we can filter off so that we only look at the tokens that we care about. So we don't have to work over the whole AST anymore. Now we can restrict it to only looking at definitions and references, and so forth and so on. And this sort of encompasses this whole concept of layering all these different tactics together to create a really efficient look, or a really efficient variable lookup. And you can do this with a bunch of different things by taking advantage of being able to reorder your data in whichever way you want by permutation or sort. Now, if you've been paying attention, you should recognize that this is not just an APL concept. Mosley and Marx talked about out of the tar pit, they talked about a model of programming, which was essentially relational data manipulated through an extended relational algebra. And essentially we're doing that, but using the syntax of APL as a really nice way of working with things. So we get some basic lessons coming out of this, and we'll go through this quickly. These are general high-level lessons. I don't want to say that I have proven these here. These are just sort of my claims to get you to think about these things at a higher level now that we've talked about the tactics. So one, I'm going to claim data hiding is a bit of a myth. So instead of that, just embrace more control over your data. And if you want to embrace more control, data encoding is critical to this efficient array programming model. And you can regain this control without losing the convenience. So in APL, all of these techniques are very convenient to use, you get the control without the convenience, the loss of convenience. And instead of having to work really hard to leverage data-driven programming ideas, if you encode your data correctly, data-driven programming just sort of falls out naturally. And by putting data structures under an array model, you keep a really nice syntax and an interaction model without losing the benefits of all of these other things like sets and searches and trees and everything like that. And if you've really, really been paying attention, you'll notice that what we've been doing here is essentially applying low-level understanding and low-level thinking with high-level language concepts and putting them at a high level instead of using them at a low level to build up a high level. And in terms of how we use this, it's very valuable if you stick to global, which means you try to arrange your code so that your objects have very good, clear, well-understood lifetimes. And you avoid like intermediately threading through these like intermediate states that are going to have partial lifetimes that are hard to follow and hard to track. Stick to temporary stuff with very short lifetimes or global stuff with long, long lifetimes. So it's easy to recognize where your lifetimes are and where your data is. And of course, take advantage of these functional programming principles to manage that state throughout your whole system when you're applying these techniques. So with that, I think we've got a few minutes for questions, and thank you very much. I will also be at the Hangout afterwards.
Yep. Thanks, Aaron, for sharing your thoughts with us today. If there are any questions you folks want to ask, you can ask them in Q&A section.
Can you hear me now?
Yeah.
Yes.
Hardware mic was off. Thanks for the talk, Aaron. I love it as usual. When you started sketching out trees, I naturally started thinking about hash array map tries, because those are the persistent data structures underlying pretty much they unify a lot of the closure, the programming model. And I think what stuck out for me was, I think all of those addresses the 64-bit words. And so I'm just very abstractly trying to relate this to that, because at one level you're talking about the same things of very general data representation, underlying data representation for and having a different view on that. So to some extent that is true in the closure implementation of HAMTs, because vectors, sets, and hash maps, they all implement these hashed interfaces underneath. Like, it's more or less the same. I mean, I don't know the entire detail about that, but ultimately, like, they are storing some data in a garbage collector environment. They are pointing to some information there. And do you see like, and ultimately it's a JVM underneath, right? So between the top and the bottom, do you think this way of thinking is applicable in like a JVM context? It's a very nebulous question, I think, but
yes. I think if I understand your question correctly, I think what my attitude on it is that these things like trees and hash maps and these modeling arrays are best used as out of bound or out of band indexing operations to support a lower level model, because very often they're overkill. Very often they're too expensive and you don't need them. So the way I prefer to structure things, even in something like a JVM, I would do this, is I would use straight up naked arrays for most things. And then and almost all the time, that's going to be way more than you need, right? Straight up naked arrays. And JVM can do that really fast. But if you need to do something else to search over those arrays, you can attach to any given naked array an implicit hidden structure that's a map, a hash, a tree, any kind of set type stuff. And you can use those to support sort of indexing over that index space more efficiently, to have different ways of finding data within that array more efficiently. But basing your array model or your object model on top of the hash map as a lower level concept, I think tends to be overkill, precisely because the overheads are way too high for most types of data that you want. I don't know if that answers the question. I don't know if that's where you were going with
Yeah,
it.
yeah. It's kind of close because that shows up in the
Hey,
benchmarks that we see
sorry,
for HAMTs.
sorry,
Any,
Aditya.
yeah.
Sorry to interrupt you. I think you can take this conversation ahead in the Hangout table since
Yeah. Will do.
we are
Yeah, absolutely. I'll hop over to the
uh,
Hangout as well.
yeah. So first of all, thank you, Aaron, for the awesome session. Yeah, thank you all. Thank you, Aaron.
Excellent. Thank you very much.